So we'll talk about mass spectrometry. We are going to we're going to go through several steps. First, we're going to talk just a little bit about theory, what needs to be done to record a mass spectrum. There's several parts to it. The first part is the ionization. So what we do in mass spectrometry is we want to measure a mass, but what we actually measure is a mass to charge ratio. Usually this is listed as M/Z. So in order to do mass to charge, we need to generate a charge. Right, so this is the ionization, and we're going to focus largely for most of the time on an ionization technique just called electron impact. And it is, it's kind of the old standard approach, but it's probably what you would use if you were doing GCMS. It's very reproducible. It gives more structural information than some of the other techniques because it is kind of high energy and it causes fragmentation. And it's also good, like with GCMS, because it's so reproducible, there's lots of big databases of spectra, and so you can match spectra and search for them and things like that. So after we go through this whole process, we're going to go back and then we'll talk more about some of the other methods at the end. Okay? After we ionize it, we'll talk about the molecular ion. So this is the ion that has all of the atoms in their highest or most abundant isotopes. And we like to get that, and from that, hopefully, we'll get information about the molecular formula. Because above all, this is what we would like to have. And then, when we generate that ion, we end up putting in excess energy into the molecule, and so it oftentimes breaks apart or fragments. And from this fragmentation, we hope to get some structural information because it will fragment following, the rules of organic chemistry. Though it's pretty high energy, so like IR, there will be ions that we won't be able to explain, right? Because a lot of high energy things can happen. So what we'll try to focus on is the molecular ion and more of the higher mass ions. They'll give us the most information. All right, so the information, we've kind of gone through this already. The information hopefully is the molecular mass. We get this in this mass to charge ratio. From that, we hope to get the molecular formula, and we hope to get some connectivity of atoms from the fragmentation. So there's several different stages in this process. So I've kind of said all this stuff already, but we're going to form the ions here. We're going to focus on electron impact. Once we've generated the ions, either the molecular ion that has all of the atoms in the molecule or the ions that have generated through this fragmentation, we then have to separate those ions. And then we have to detect them in the end. So we essentially count the ions that come through.
What is atomic connectivity from fragmentation?
Well, the atomic connectivity is basically the structural information, right? So depending upon how it fragments, what pieces fall off, we'll hopefully learn about what kind of pieces are in our molecule. All right, so here's kind of a diagram of what's called a single sector magnetic mass spectrometer. So this is kind of a basic setup, and I was reading this morning this kind of magnetic sector instrument was essentially developed back in 1922 or something, and it was the development of this led, in part at least, to a Nobel Prize and stuff. But the technique is still used, even though it was developed one of the earliest ones. So in general, the way that this works is we have the sample inlet over here, and there's various ways to introduce your sample into this system. In electron impact ionization, we put the sample in, it then volatilizes or evaporates into the ion chamber. Okay, so that's kind of one of the requirements to do this technique is the molecule has to have some volatility. So that's kind of a limitation. But so it volatilizes, goes into this thing here. It's called the ion chamber. And it floats in here essentially, and there's this filament, which is, we can think of two filaments called an electron gun. So it's shooting electrons across this space. And the molecules can get hit by the electrons, and it's going to put a lot of energy into them, and then they're going to lose an electron. So the way that we, I'll draw it out on the next one. So we generate ions here from this electron beam. And then we have this whole mixture. We'll have, neutral molecules that weren't ionized. We'll get some cations, maybe some anions all in here. But the cations are the ones that we're going to analyze. And so the way that this is set up is on the back of this, they have this positively charged repeller plate. So if we got cations and we have this positive plate, it's going to drive the cations the opposite direction. We have these negatively charged accelerator plates, and so the ions are going to shoot down this tube. And the voltage between the positive and negative is going to control their velocity, and their velocity is going to be related to their mass-to-charge ratio. So as they shoot down here, they're going to go into this magnetic field, and their trajectory gets deflected based upon the magnetic field. And so once they come around, they get deflected, and they go down this analyzer tube, and for a given voltage on the acceleration and the magnetic field, really only a certain mass-to-charge ratio is going to make it through this exit slit. Okay? So the radius of the deflection, or of the curvature there, I was looking these up this morning. I saw some slightly different versions of this equation, so I don't know which one was exactly this right, but I think the trend is going to be the same anyway here. So the radius equals the square root of the mass to charge times 2 times V over B squared. Okay, so V is the voltage. This is across the accelerator plates from the repeller to the accelerator plates, this voltage difference. B is the magnetic field. And so if those are held, if those are all set, then the mass to charge ratio is going to affect the radius of the curvature. Okay? And in general, if we look at this, then lower mass to charge ratios are going to be deflected more. Okay? And higher mass to charge are going to be deflected less. Okay? So what we do essentially is we can scan either the voltage or the magnetic field and essentially bend this, array of ions across the exit slit and scan through all the different mass to charge ratios. Okay? So once they come through, then we can collect them, or the detector, and we'll just record how many of each of the ions that we get. All right, so a couple of other things is that this ion chamber is under high vacuum, and the vacuum is for a couple of different reasons. One is that it helps volatilize the sample. Okay. And the second thing is it helps make sure that the fragmentation reactions that take place are all unimolecular. So we just want the molecules to break apart. We don't want them, in this case, bumping into each other and reacting with each other. All right, anything else that we should say here?
Unimolecular reactions mean that we don't want them to have reaction with the atomic atmospheric oxygen or nitrogen or something like that.
Right, nothing else.
Oh.
Right, so essentially we can think about it as limiting it to unimolecular reactions, because under a high vacuum there's going to be a very small concentration of molecules, and they're all going to be kind of spread, spaced apart. And so unimolecular just means that the reaction rate depends upon only the concentration of one species, right? And so that one species would be the analyte. All right, so here's just kind of a summary. So in this ion chambers, as the sample is volatilized, the molecules are bombarded with an electron beam. High energy radical cations are formed, so we could draw it down here. So here's our analyte. I'm going to draw it as M. We're going to essentially shoot it with an electron beam. It's going to get excited, and it's going to eject an electron. Okay, so it's not really absorbing the electron that it gets hit by. It gets energized, and then it ejects an electron, and it generates then a radical cation, which we usually draw like this. So we can think about it as if we had a molecule like this that just had a pair of electrons. When it ejects an electron, we're just showing that electron left, and the plus is kind of the vacant spot where the electron was lost. Okay, so this radical cation here would be the molecular ion. Okay, because it's going to contain all of the atoms of the molecule in their highest, with the most abundant isotopes for each of those atoms. Then what can happen is, if this is energized, is that it can fragment. So we can lose, I'm going to draw it just as an X, we're going to lose some neutral fragments.
We will not detect them, right?
Correct. We only detect, in this technique, we only detect the cations. Okay, so then we're going to generate some M minus X with a plus. Usually this neutral fragment, most commonly, but we'll see some exceptions, is a radical that we lose. And so then our fragment ions are no longer radical. Okay, we'll talk about some language to talk about these in a minute. So these are called the fragment ions. Right, and then we have to separate them, and we have to detect them. Okay, so we're going to have several stages here. We're going to first focus on this molecular ion, and learn some techniques by which we might be able to determine a molecular formula from that. Okay. Then we're going to talk about fragmentation mechanisms, and then we'll be able to start using this as a way to determine structures. Okay. All right. So the molecular ion, like I said, is the ion that contains all of the atoms of the molecule in their most abundant isotopes. Okay, so what criteria do we have for a molecular ion? If we see an ion in the spectrum, how do we know it's the molecular ion?
It's the largest I'm seeing.
Right, it has to have the highest mass, or highest mass to charge ratio, I guess. For electron impact, it has to be what we call it has to be a radical cation. Which we also will call an odd electron, an odd electron ion, okay, because it has M plus, it has a radical, okay? And 3 is that it must be able to yield all of the important fragment ions through logical cleavages, logical losses. By logical losses.
So, are there situations when that doesn't happen?
Not if it's the molecular ion.
Well, okay.
However, because we're putting so much energy into this molecule in the ionization process, there's going to be situations where the molecule fragments so easily that we don't see the molecular ion. Then, when we're looking at the spectrum, the highest mass ion that we see in the spectrum may not be the molecular ion, right? So it would be the highest mass to charge, but it may not be a radical cation, and it may not be able to yield the other fragments in the spectrum.
Okay.
Right?
That
So
makes
they
sense.
may come from something that was higher,
Mm-hmm.
and we can see that, yeah. So that's why we have to have those in there.
That makes sense.
Okay, so what are these odd electron ions and why are they important? Okay, so there's a couple of different ways that we can envision this ionization process. Okay, so let's say all we have is single bonds, sigma bonds. And so I'm going to just draw this sigma bond like this with a pair of electrons instead of a bond. So we're going to shoot this with an electron beam, ionize, it's going to eject an electron. And so the molecular ion we could draw like this. Okay. So we'll talk about fragmentation, but you can imagine already that if you lose an electron from that bond, it's going to weaken that bond, right? And it's going to be able to more easily break apart. Okay, so now if we just had an alkane or something like this, there's kind of a competition on where it can ionize. We got a lot of sigma bonds that could ionize, so it's not only the one that I'm drawing. We can also have ionization that takes place on non-bonding electrons, and this is more common. So we'd have some radical cation located on the oxygen here. They can also take place within pi bonds. Like this. So one thing when we're doing our structure determination is that another way to tell if an ion is the molecular formula or the molecular ion, if we get a formula from it, that odd electron ions will have, I don't need to do it that way, integer number of unsaturations, if we want to do that calculation. So for example, if we had a molecule like this, right, that has a molecular formula of C9H10O, and we calculated our unsaturations, the unsaturations would equal 5. Okay, but when a molecule like this is analyzed in the mass spectrum, it can cleave at this position right here. And we'll talk about these mechanisms, but we might generate, so this would be, the molecular ion would be something like this, but it could cleave and it would give us some other ion. It's got a couple of different resonance. We'll just draw it like this. So this ion has a formula of C7H5O. But if we calculate out its unsaturations, what does it have?
Still 5. Right?
Is it?
Still 5?
Is it?
Well, there's 4 from the benzene ring.
It's about half.
5.
But use the formula. The molecular formula, not just looking at the structure.
Yeah. It would, yeah. 5.5.
Right, because it only has 5 protons now. So if we see an unsaturation number of a half, then we know that this has to be a fragment ion, or what we would actually call if this is an odd electron ion. Oops. This one down here is an even electron ion.
Are fragments always even electron ions and molecular ions the other way?
If they're generated through the cleavage of one bond. We'll see if it cleaves multiple bonds in the process and does some kind of rearrangement or something, then an odd electron ion can generate another odd electron ion. But if we're doing single cleavages, then we'll go from an odd electron ion to an even electron ion. All right. Now, for most elements, there's a relationship between the most abundant isotope and the valence number, so how many bonds it can make. For example, they're either both odd or both even. So odd are things like hydrogen, right? Has I'd say it has a abundance. Isotope is 1 and the valence is 1. Okay? If we have both odd, that's 1. Both even would be something like carbon 12, right? Has isotope is 12 and the valence is 4. Right? Or if we have oxygen, 16 is the most common, and its valence is 2, right? The number of bonds that it can make. All right, so for these molecules, their odd electron ions will have an even mass. Okay, so we can just calculate out the masses. Water has a mass of 18. Methane has a mass of 16. Something like phenol has a mass of 94. All right, so all of these odd electron ions, which would include their molecular ions, will have even masses. Okay? The exception to this rules up here is nitrogen. Okay? Because nitrogen has an isotope of, what am I looking at here? Why did I do that there? Nitrogen 14, right? And it has a valence of 3. So if we calculate out the masses of nitrogen-containing molecules, like ammonia has a mass of 17, something like ethylamine, C2H5NH2, has a mass of 45. Okay, so these odd electron ions have an odd mass. It's an even mass. Okay, so this leads to what's called the nitrogen rule. And what it says is that an odd electron ion will have an even mass if it contains an even number of nitrogens, including 0. But if it had 2 nitrogens, it would have an even mass as well. Okay? An even electron ion containing an even number of nitrogens will have an odd mass. So this is the molecular ion. This is some fragment ion. The opposite part of this is that we could say that a odd electron ion that has an odd number of nitrogens will have an odd mass. Okay, so let's put that down here. An odd electron ion will have an odd mass if it contains an odd number of nitrogens. All right, and then likewise we could say an even electron ion containing an odd number of nitrogens would have an even mass. Right, so it's just going to be opposite. Right? So here, this would be the even electron ion with an even number of nitrogens will have an even mass. Okay, so it's just, if we have no nitrogens, it goes from even to odd. If we have an odd number of nitrogens, it goes from odd to even. Okay? Though, of course, it can get more complicated. You know, for example, if you have a molecule with 2 nitrogens in it, right, then the molecular ion, should it be odd or even? Even. And if it fragments, if it loses a fragment that contains no nitrogens, it'll still have an even number of nitrogens, so then it would go to an even mass, right? But if it fragments and loses one of the nitrogens, yeah, then it's going to switch to the other one. Okay? So, this is one of those things that if we know we're looking at a molecular ion and it has an odd mass, then we're like, it has to have nitrogen. Okay? If it's even, we don't, usually in the ones we'll look at, it won't have any nitrogen, but it could have 2 nitrogens or an even number. Yeah. Okay? I know, you can start writing out a whole bunch of scenarios of how those all are, and it gets really complicated. All right, so the next part of it was that we had to be able to generate the fragment ions through logical losses. And one thing that helps us here is that, not all losses are logical, right? So we could, for example, lose a hydrogen atom, right? Maybe we could even do some kind of step, rearranges or something, lose 2 nitrogens, but there's nothing really in an organic molecule that is logical loss of 3 or 5 or 7 or 10, right? There's just no way to use hydrogen and carbon and oxygen and nitrogen and halogens or phosphorus or any of those things and lose masses actually between 2 and 15. So uncommon would be losses from 3 to 14. And then if we look at this up here, from 21 to 25, these are going to be really uncommon. There's just no way to use the atoms we have to come up with ways to lose those masses. And so this table, has some ways to lose some of these. So like the loss of 15 is almost always the loss of a methyl group, right? If we go down here, 29 is commonly loss of, an ethyl group, right? So these are logical losses. Loss of 35 could be loss of a chlorine, things like that. So this is something also that, I'll get ahead of myself a little bit here, but, excuse me. Let's say we had some molecular ion, and it could lose 15. Let's just say that this is 100 mass, okay? Then it would give us a mass to charge equals 85. And let's say it could also lose 29. You can use a methyl or an ethyl. And so this would be mass to charge of 71, right? So if we didn't observe this, right, then we're left with masses of 85 and 71, right? So if we think that 85 is the molecular ion, the first thing we'd think is, it's odd, so it has to have nitrogen. And then we could think about, can it generate the other fragment ions through these logical losses? So 85 to 71, what loss is that?
14.
It's minus 14, but 14 is an uncommon loss from a molecular ion. You can't, right, 14 is typically a CH2 group, but you can't just lose a CH2 group out of the middle of a molecule. All right, so this would tell us that this is not the molecular ion, right? Because it doesn't satisfy the criteria that we talked about.
So what are the uncommon ones? Just from 3 to 14 and 21 to 20?
No, well, you could look at this list, and probably I brought this from a list that's even bigger too.
Mm-hmm. So we just subtract the biggest mass charge ratio from each
Right,
other.
so yeah, what we'll
And
often
look at those values to see if it's in the list of uncommon.
Right. Well, we won't always just be looking for what's uncommon or not. We'll be looking to see, we'll be subtracting these masses, if we know the molecular ion, to the fragment ions usually, and, we'll see what mass is lost. And so we'll see if that mass, matches some known fragment. But there are certain masses that, we just will never lose, right? So if we're trying to fit that into our structural analysis, then we know that, that something's not right. All right, so the abundance of the molecular ion depends upon the stability of the molecular ion, okay, and the amount of energy that's put into it. So typically, these experiments are all run with a certain number of electron volts in the electron beam, but it can be varied. If your molecule fragments too easily, sometimes they can do it with a lower voltage. So it depends upon the stability of the ion, and in general, the stability of the ion parallels the chemical stability. All right, so the most abundant, or the types of molecules with the most abundant molecular ions, will be things like, aromatic compounds, conjugated alkenes, any of these where the cation could be delocalized, right, and stabilized. Cyclic compounds might come next, just because I think it's harder to break apart. Even if you have a ring, if you cleave it once, it still has the same mass, right, until it breaks apart. And then down below this are just going to be, acyclic things.
So these are the most abundant molecular ions.
Right, so these are going to be the ones that have, it's easier to see the molecular ions, right? All right, so let's look at a spectrum. All right, so here's just a spectrum of this, this is like dodecane, right? Oops, that's not what I wanted. C12H26. All right, so what do we see here? So down here on the x-axis, we have mass-charge ratio. On the y-axis, we have relative abundance. Now, the spectrum is always adjusted, so the most abundant ion is set at 100%.
So the 43.
Yes. So 43 is the most abundant ion, and so it is set at 100%, and this most abundant ion is called the base peak. Okay, so even if you had a molecule that doesn't ionize very good and doesn't fragment very good, and it has a low level of ionization, we still adjust it so the biggest one is 100%. Okay? So the highest mass, right, 170, it's an even mass. This should be our molecular ion. We could add up C12H26 to confirm that. Okay, so this is the molecular ion, and all of these down here are fragment ions. All right, notice that they are all odd. Okay, what else do you notice about all those ions?
They're all separated by 14.
Right, they're all separated by 14 mass units. Does that mean that it goes from 170 to 85, then to 71, then to 57, then 43, and then 29? No. What it likely means is that this molecule is just going to be fragmenting at different places. Well, let's see, 1, 2, 3, 4, 5, 6. This is in the middle. So we could draw it like this. And this would be 85, right? Because it's split in half. Down here would be 71. If they split and the charge goes to that side, so the arrow shows which side the charge is going on to, right? This would be 57, 43, 29, and usually we don't even, when we get down really low, we're not going to say, oh, look, there's an ion at 15. We must have a methyl group, right? We're going to be more interested in the higher mass groups, the loss of a methyl group, not the presence of a methyl. Okay? All right, so what we see, for one thing, is when we get a cleavage, we're seeing that we're losing the larger radical, right? We don't see up here a big ion at 155 for the loss of a methyl group, right? We're seeing if it's going to cleave, then the cation is usually going on to the smaller fragment, and we're losing a larger radical. Yeah.
With the fragmentation that you've drawn out on the top, is that the same? Would that be represented as the same molecule getting chopped smaller and smaller, or is it just different cleavages on different?
Just different cleavages. So we're shooting this thing with an electron beam, and all of these carbon-carbon bonds have roughly the same energy. The ions are going to be roughly the same stability. They're all primary carbocations that are being generated, right? And so it's just a competitive process, right? It's just ionizing at different places, and it's fragmenting wherever it ionizes.
Why we don't have any fragments from 85 to 170?
Yeah, so I think the rule, and I'm not quite sure the exact, process here, is we usually observe the loss of the larger radical. So if the cations are all roughly the same energy, we'll see the loss of the larger radical. If one cleavage leads to a more stable cation, then we see more of that. All right, and that's on this next one. All right, so if we have a branched alkane, we see something very different. First off, I think this one still has the same formula. First off, we see no molecular ion. All right, so this molecule is fragmenting more easily than the previous one. Okay, and it's doing that because it can generate a more stable fragment ion. Okay, and so we see that 57 is the base peak, and that's the main ion that we're seeing, right? And if we look at this, we would be cleaving it at this position, and essentially it's creating this tert-butyl cation, right? Which is the most stable one that we can easily form here. All right, and if it's going to cleave at that position, here, we're not going to see the cation going to the primary side, right?
So when we don't have no molecular ion, it causes any problems for the detection or something like that?
I think that it generates and it cleaves very rapidly, and so fast that there are no, molecular ion that makes it all the way to the detector. So of course this would be this is a much more difficult situation, right? Because if we're relying on mass spectrometry to give us a molecular formula, then we don't get that information here. All right, so let's talk more about the appearance of this molecular ion. One is that these ions are not just single peaks, single ions. There are clusters of peaks. All right, and these clusters are created because every molecule is a mixture of isotopes. Okay, and we can see, because they're a mass unit apart, we can see the presence of all of the isotopes of a molecule. Okay? The common isotopes for organic chemistry are shown here, and some, have very characteristic isotope patterns, right? So, for example, carbon, we know that carbon-12 is the most abundant. So here all the most abundant isotopes are set at 100%, okay? And we learned before, when we were talking about C13 NMR, that the C13 isotope has an abundance of 1.1%, okay? So what that means is for every carbon atom in the molecule, there's a 1.1% chance that it's going to be a C13 atom. Okay? We're going to be able to use this to help us determine molecular formula.
We are able, we are not.
We will be able to. Yeah. So other ones, deuterium has a small contribution. Oxygen, has the most abundant of O16, but notice O18 has a 0.2 relative abundance. We'll be able to see that, and we can actually use that to help predict the presence of oxygen in the molecule. Silicon actually has three fairly abundant isotopes. Sulfur has this, let's call these, I think this book, we can call these, if we just call this A, this is A plus 1 and A plus 2, okay? And really the easiest ones to pick out here are chlorine, where it has a 35 is the main abundance, and 37 is a 32.5% abundance. So this is roughly a 3-to-1 ratio. And bromine, right, has 79 to 81, and they are almost in a 1-to-1 ratio. Okay, so in these cases, we can clearly see these two ions. And we'll look at some examples now that will show us the presence of those atoms in the molecule. Okay, so for example, if we have a bromine in the molecule, we see here the molecular ion, right, has 164 and 166, and these are roughly in a 1-to-1 ratio, right? 135 to 137 also has bromine in it, so what are we losing here? 146, so what you need to do when you do this, too, is 164 goes to 135, right? So what's that loss of 29? Also, 166 going to 137 is also loss of 29, right? So we're just showing the loss of probably an ethyl group here, and it can happen with either the bromine 79 or bromine 81, right? But what about 85? Does that have bromine in it?
Nope.
No, because at that point, the bromine has been lost, right? And probably if we go from 164 to 85, that's loss of 79. And if we go from 166 minus 81 gives us 85. All right, so we've lost the bromine, and so we no longer have those two isotopes in the molecule. So we know that there's no bromine at this point, or any of these other ones. What about this one? Does that look like it has bromine in it?
Too small.
It's too small, right?
Which does look like
It, it does,
Yeah.
but there's not enough mass there to have bromine, right? Okay. Chlorine, right, is going to be something similar. So we have 156 and 158, and these are roughly in a 3-to-1 ratio. Okay, so that tells...
You're integrating their peak area, something like that?
Not really area, it's the peak intensity, because these ions don't really have an area.
Oh, we can say about...
It's just a plot of how many ions there were. So in order to do this, well, with this we could probably estimate it, but if we're really having to analyze these, we'd get a printout of the ion abundances. All right, so notice that in this case, too, none of these other ones here have chlorine. So this has chlorine in it. These have no
How do you say
chlorine.
that?
Huh?
How do we know that there is no chlorine in it?
Because there's no second isotope in a 3-to-1 ratio.
Oh, I see.
Right. So both of those have fragmented in such a way that they've lost the chlorine. I think this one we'll come back to later when we know something about fragmentation, and we'll look at this again. All right. So we can have, other different combinations of these halogens as well, and come up with all these different ones. So here's a single bromine, here's a single chlorine, right? And this has all these different, if there's two bromines, right? So this would be the 79. The middle one would be 79 plus 81, or 81 plus 79. And the higher one would be 79. No. 81 and 81. This one would be 79 and 79. This would be 81 and 81. Right? So a 1 to 2-to-1 ratio.
a triplet, if you will.
Right. If you get 3 bromines, you get a quartet. Here, let me pause this for a second. All right, so not only the halogens can you calculate, right? All right, so one way to come up with a number of carbons is to use this formula here. So we can calculate, so this is basically what we were doing. The number of carbons equals the relative intensity of the n+1 peak, divided by, this is essentially 1.1%, right, times the relative intensity of the molecular ion peak, or the ion peak. Oftentimes what we'll do is we'll scale these up to 100%. But this can work for even if it's less than 100%. So if we have this one here, then we have the number of carbons equals, I estimated here, so this is M plus, this is M plus 1, is roughly 11%. So we've got 11 divided by 0.011 times 100% for the main one. And so this comes out to 10 carbons. All right. If this was scaled down, for example, if the M plus was at 50% and the M plus 1 would then be at 5.5. So it's just scaled down, but their ratio is the same. This would still work the same because the number of carbons would be 5.5 divided by 0.011 times 50. Right, so this still equals 10.
The scale doesn't matter.
Scale doesn't matter. Though when we start using the McLafferty approach, what we'll usually do is if the peak that we're interested in is at 50% and the isotope is 5.5, we'll scale these up to 100%. And then it would be like this up here. Yeah, it's easier to do it that way. Okay. We're almost done. Okay, so this is just the same one we were talking about already. Print out, oops. All right, so let's just read through this and we'll just call it good for today. We won't work any problems yet. So this is essentially the McLafferty approach to determining molecular formulas. All right, and a lot of times we won't, I don't know how many times you'll do this, but I think it's good to learn this. Just you gain an understanding of how the isotopes are all working together in there. So the requirements to use this technique are that the spectrum has to have strong ions with a high signal-to-noise ratio.
What is strong ions? What do you mean by spectrum?
Well, they go together. So it can't be a real noisy spectrum where you may have noise superimposed upon the ion abundances, right? We need to have them strong enough with high enough signal to noise that the noise isn't going to affect the abundance of those ions. And we need some kind of a printout of the ion abundances, right? We need to know what the abundances are. All right, so the approach is going to be, we're going to choose some ion. Could be the molecular ion. Could be some other fragment ion, but it has to be free of interfering peaks. So if we have overlapping ions, and so we have different ions that are contributing to the abundance of a given peak, then that's going to be very hard to calculate. We're going to write down these three, M plus 1, and M plus 2. So we're just going to make a little table. And we're going to write in the abundances, and then we're going to normalize the M plus to 100%, right? And the other ions proportionally. We'll then first look for the presence of these M plus 2 or A plus 2 or whatever, M plus 2 ions. So chlorine, bromine are the easiest ones to identify, but we can also identify the presence of things like sulfur and silicon, because theirs were at least 2% or 4 or 5%, and that's going to be, very big for an M plus 2. Once we've accounted for those, then we're going to determine the number of carbons based upon the size of the M plus 1. Once we've accounted for that, then we can look for oxygens. And then after we've added all those other ones up, and we've added the mass up to a point where it makes sense, then we can add in hydrogens to make up the mass. Right, so we don't want too many. We can't have too many hydrogens where it's beyond the maximum, and we don't want too few, or it would be just impossible to come up with that number of unsaturations. All right, so this will be a process. We'll do some practicing on how to use this, okay, before we go on into fragmentation mechanisms. So. And I'll look over your shoulder and berate you if you're not following the rules. Yeah. All right?